Hi, it's me again, Mrs. Beck, with your math lesson of the day. So today we are going to focus on what to do when you can't solve by factoring. So to start off today's lesson, we're going to recall if we can factor. So I want you to take a look at this problem and I want you to solve by factoring. So take a moment, answer the following question. All right, so hopefully you did this. You realized it was simple factoring. There was no number next to the x squared, so you put two parentheses, bam and bam, x and x. You need factors of 50 that give you 15. That's a positive 5 and a positive 10. Remember, we are solving at this point. So yeah, we factored it, but now we need to solve it. So if this was 0, if y was 0, what are the x values? Well, the lucky thing is we know about factors and zeros that they are opposites. So x equals -5 and -10. That's what we get when we solve. But if you look at a problem like this, x squared plus 7x plus 5, I look at 5. I want to say, what's the factors of 5? They're 1 and 5 and -1 and -5. None of them add up to our middle number 7. So this isn't factorable. But look, it's still a solution. So you don't want to say no solution, because here is the graph of this, and there's the x-axis, and it does go through the x-axis right here and here. That makes those my x-intercepts, which makes those my solutions, which makes those my roots, which makes them my zeros. So there are solutions. It's just that they're not numbers that we can really identify. They're definitely a weird fraction. It's not on a line anywhere. It's not halfway through a line anywhere. It's like off of -6. I can't tell what the number is, but it is a number. So we are going to now learn what to do to find this number that does intersect the x-intercepts. So how do we find this number? There's a couple different options on how to solve quadratics. So the options are solving by factoring, solving by taking the square root, solving by completing the square, and solving by the quadratic formula. You're going to want to write this down in your notes. So solving by factoring can only be used to find the zeros when the equation is factorable. Duh, that makes sense, like above. Solving by square root, I'm not going to teach you how to do, but solving by square root only works well when the b term is 0. And we know that's not the case all the time. So this doesn't really work every time. It's just in a couple different occasions. Solving by completing the square. So you heard completing the square as a process before. That's actually how you can go from standard form to vertex form. But it's only best for solving quadratics when a equals 1 and b is an even number. If those two things aren't happening in the equation, then you're working with fractions and it's just going to take a long while and it's a pain in the butt. So we are also not going to go over this process because the last way to solve a quadratic is by quadratic formula. And the quadratic formula works every time. It's just a little bit long. So in this class this year, why would we learn these two processes if this works every time? Well, we're not going to. We're going to learn the quadratic formula. Obviously, factoring is easier, and you're going to see in a while just how long the quadratic formula takes. But this is what we're going to focus our lesson on today. Before we get to solving quadratics, we are going to talk about what kind of solutions we may find when we solve. So you have this table in your notes. It's kind of off center. It's going to bug me. Okay. All right, we're just going to get over it and we're going to deal with it, right? We're just going to deal. Mostly me. I'm the only one having issues with it, probably. Okay, so when we solve quadratics, when we did the intro to quadratics unit, we noticed that sometimes it hits the x-axis once, sometimes it hits the x-axis twice, and sometimes it doesn't hit it at all. So we're going to talk about these types of solutions a little bit more in depth on what they look like number-wise. So When it doesn't hit the x-axis at all, if we're looking at this graph like this, there's actually solutions. They're just imaginary. Yeah, I sound crazy by saying imaginary, but imaginary numbers are legit. I swear. I didn't make them up. So if it doesn't hit the x-axis, there are still solutions. They're just two imaginary solutions. Now, these solutions are always conjugates of each other. So that's a new math term. Conjugates of each other just means opposite signage. So, for example, I know you don't really understand imaginary numbers yet, but imaginary numbers are written by i's. So, a positive I and a negative I are conjugates. A positive 2i and a negative 2i are conjugates. Imaginary numbers also have two parts. They could have a number part and then the imaginary part. So in this case, 1 plus I, its conjugate is actually 1 minus I. The sign of the imaginary part is the opposite. So we'll denote that by writing that down. Also, it could have some radicals in there. So like 2 plus I root 5, 2 minus I root 5, they're conjugates. So whenever there's an I in it, that means they are imaginary. That means that the graph doesn't actually hit the x-axis. It's got its zeros in imaginary land. What the equation may look like is something like this. Now, until we actually solve, you wouldn't know that they're imaginary. But if this is the case and these are the answers, you need to solve using the quadratic formula. And we have to learn imaginary number rules, and we have to learn how to reduce radicals again, which is something you did in geometry, but we will go over briefly in this lesson as well. Now, we saw this before where there's one rational solution. To be fancy, though, we are going to say that there's one rational solution with a multiplicity of two. So that means x equals 1. That's the only solution. X equals negative 1/2. That's the only solution. It only hits the x-axis twice. The reason why we say multiplicity of 2 is because these kind of problems, these solutions can be found by factoring. And if we look in this is factorable by x minus 2, x minus 2, right? Factors of 4 that give you negative 4. Which means if we go to solve, we get x equals a positive 2 and a positive 2. Do you see that's what I mean by multiplicity of 2? That 2 is written twice, not 2 times 2, but it's a root twice. It comes from two different factors. So on the picture, it only looks as 1. We only have to write it as 1. But when you do those factors, that means it's got 2 of them. And again, if there's one rational solution, that means that the equation could be factored. Two rational solutions. We've seen this plenty of times when it's like 2 or negative 3 or negative 1/2 or 5. And that's when they're blatantly on the x-axis. In fact, they're so blatant that we could tell the numbers because it's hitting a tick mark or it's a half or 2/3, some fraction that is obvious. We're going to go over that in a second with the idea of rational and irrational, which is something you've learned in algebra, but we're going to go over again. And again, if you have two rational solutions, two whole numbers or fractions, that kind of equation is factorable. So you find these solutions by factoring again. So if you look at this problem, factors of 6 that give you negative 7 are x minus 6 and x minus 1, giving you x equals 6 and 1. Now, there is another case, just like we saw in the front page, where they have answers on the x-axis, but the equation is not factorable. And that means there's numbers that are real, they're not imaginary, that are the solutions, but they're irrational. Irrational means that you can't be written as a whole number or a fraction. That means that you're a decimal point that goes on forever. AKA, it's written as a radical. So we're going to get radical answers here. Get it? Radical answers, Yeah, okay. But these are also represented as conjugates. So if root 5 is the answer, negative root 5 is the other answer. These also are written with part number and in part radical. So 4 plus 2 root 2, its conjugate is 4 minus 2 root 2. So these are the answers we're going to see if the equation is not factorable. And we're going to get these by, again, using the quadratic formula. And then we have to recall all these reducing radical rules as well, which, again, we will go over in the next page. So these are all the types of solutions that you could have. So basically, you're either getting 2 answers or 1 answer. Your answer can be a whole number. It could be a fraction. It could have a radical. It could have radicals and i's. But these are all your options. And then if you look down here, these are how we should solve them. So again, factoring so much easier than what I'm about to teach quadratic formula. But we're going to go over the quadratic formula now so we can learn how to find these. Before going over the quadratic formula, I do need to go over the imaginary number rules and the reducing radical rules. So on the next page of your notes are what I call reducing reminders. So imaginary numbers come from this fact that you can never have a radical that has a negative number inside, which makes sense because if you look at something like the square root of negative 4, well, that means you need to find 2 numbers that are the same that multiply to get 4. But if it's a negative, that means one has to be a negative and one has to be a positive. So there are not 2 of the same numbers that will ever get you 4, because the regular square root of 4 is 2, because 2 times 2 gives you 4. But negative-wise, you can never get that negative. So negatives aren't allowed in the radical. So one day some mathematician was like, hey, I'm doing all these problems and these negatives are still popping up in the radical. Let me assign something called imaginary numbers to it. And the word imaginary starts with an I, so that's where we started denoting imaginary numbers with I. So all that's basically saying is if you see a negative under the radical, you are not going to write the negative under the radical anymore, and you are going to put I out front of the radical. So in this case, this would be I root 4, and the square root of 4 is 2, so it would just be 2I. In this case, there was a negative next to 11. We just pull the negative out and make it an I. That's the only fancy part about imaginary numbers. Now, here's a quick reminder on regular radicals themselves. This is how we reduce radicals. You look at the number inside the radical and say, is this number divisible by any perfect square? Well, yeah, it is. This one can be divisible by 25. So I could break down 50 by saying the square root of 25 times the square root of 2. And we all know the square root of 25 is a perfect square because we chose that number to break it down. So then we have 5 root 5 because the square root of 25 can be written as 5. That's how you break down and reduce radicals. So I'm going to ask you a couple questions now on how to reduce radicals. So we're going to stop the ed puzzle, and here we go. All right, now that we're back, I also want to go over the full notation on how your answers should look for this. So there's going to be a lot of mumbo jumbo, and answers are going to look really weird like this. But it's important to note that this is the order that things should be written at. The radical should be last. Next to the radical should be the I, if it is present. And next to the I should be the whole number that was taken out of the radical, if possible. We're going to see the plus and minus because that's going to be in our quadratic formula equation. And then if there's a number, we can't combine regular numbers with radical numbers or imaginary numbers. So they must stay separated. And then if there's a division bar, we leave that on the bottom as well. Notice we can't reduce this any further. We're going to talk about reducing in a second. So 2 and 2, you guys really want to cross off, but you can't because the 5 is not divisible by 2. So to talk about reducing the fractions with radicals, we can't reduce 10 and 50 because 10 is under the radical and 50 is not. They're not the same type. We can't reduce them. But 5 and 50 are both numbers. Not 5's not under the radical. So if 5 and 50 and 10 are all reducible, then we can reduce. All three of these numbers have to be reducible. Like up here, these three numbers were not all reducible, so we couldn't reduce. These are all divisible by 5. So 10 divided by 5 is 2. 5 divided by 5 is 1. So we didn't put the 1 there, but the i's still there. And 50 divided by 5 is 10. So these are all reducing reminders that will get us to the end of the answer when we do the quadratic formula. Right now, they seem out of context to you, but don't worry. Once we start the quadratic formula, you're going to see how these are used. So here is the quadratic formula. It's this baby right here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And now these b's, a's, and c's are all values, all numbers that we get from the standard form of a quadratic. Remember, the a is next to the x squared, the b is next to the x, and the c is the constant. So in this, there should never be any variables left. These should be all numbers, and then they should be reducible. They're not going to be fully reducible. We're going to see something like we just did on the last page, but these should all at least be numbers and then an I throw in there, here and there. This is how I remember the quadratic formula, and you might think I'm crazy, but who cares? So I always remember it as a bad boy, get it, a negative b, a bad boy couldn't decide, because it's a plus or minus, to go to a radical party or not. He was being squared, so he got rejected, minus, by 4 awesome chicks. The party was all over by 2 a.m. That's how I remember the quadratic formula. Feel free to use it. Feel free to also look up other hacks to remember the quadratic formula on YouTube or on the internet. They're all over the place. Everyone has their own kooky way to remember it. There's even a song, but I'm not so musically inclined, so I stick with my little story. All right, so here are the steps on how to use the quadratic formula. And again, I'm going to warn you, the reducing part takes a long time. Other than that, we are going to make sure the equation is in standard form and put y equals 0. Because remember, we're solving for solutions. We're solving for x-intercepts. So we find x-intercepts when y equals 0. So if we look at all of these problems, they are set up in standard form. Notice how the y is on one side. We got the x squared term first, then the x, and then the constant. So I don't have to worry about number 1 so much in these problems, but sometimes you may. So let's zoom in a little bit so we can get some work done on question 1. So first we're going to identify what is the a value, b value, c value, and then what is b squared and what is 4 times a times c. So this is how I always want you to start out. This is how you can keep the neatest work possible. On the very side of the problem, you're going to write a equals, b equals, c equals, b squared equals, 4ac equals. And then we're going to plug in what those values are. So a is 1, b is negative 1, c is 2, which makes b squared negative 1 times negative 1, which is a positive 1. And it makes 4ac. So 4 times a is 4 times c is 2. So 4 times 2 is 8. Now we're going to plug that into our quadratic formula. So looking at above, x equals negative b. So negative of a negative 1 is a positive 1 plus or minus the square root of b squared minus 4ac. See how I just picked these numbers up and put them in the spots from here. All over 2 times a, which is 2. So this is where all the reducing occurs. So we have a 1 plus or minus, and then we have a 1 minus 8, which is a negative 9 over 2. We're still not done, and here's why. We have a negative under the radical. Negatives under the radical are bad. We just learned about them. They're so bad that we made them imaginary. So we're going to rewrite that as plus or minus I root 9 over 3. Now we have to double check that we can reduce the radical. So if you look at the radical, it says the square root of 9. What is the square root of 9? That's right. The square root of 9 is 3. So again, we're going to rewrite this as 1 plus or minus 3i over 3. Now, if you look, a lot of you really badly want to do 3 divided by 3 and cross these out, but you can't because all 3 of these numbers have to be reducible, and 1 and 3 are not. So your final answers come from this. X equals, remember we should get 2 answers. X equals 1 plus 3i over 3 and 1 minus 3i over 3. Answer 1, answer 2, these are conjugates of each other, like we've said before. These are our final answers. And if I was to graph this, they would not hit the x-intercept. Now we're going to try the next one. Note that these answers are messy. That's okay. So let's try number 2. We want an A, a B, a C, a B squared, and a 4AC. A is 1, B is 7, C is 5. B squared is 7 times 7, which is 49. 4AC is 4 times 1 times 5 is 20. Now we're going to plug in the values looking at the quadratic formula. So we're going to write x equals negative b, which is 7, plus or minus the square root of b squared, which is 49, minus 20, because it's minus 4ac, all over 2 times a is 2. Now we're going to continue to reduce. So we have a negative 7 plus or minus. We need 49 minus 20. So 49 minus 20 gives us, well, 4, that's 29. Should be 29. All over 2. So now we have to check. Can we reduce the radical? 29. Can we break that down into a perfect square times a number? We can't. It's not reducible. There's no numbers here and here to reduce either. So our final answers are negative 7 plus the square root of 29 over 2. And then its conjugate of negative 7 minus the square root of 29 over 2. Again, these answers look like a mess, but that is perfectly fine. These are numbers. If you type this in the calculator, it's a decimal. Can I plot a decimal on the x-axis? Of course I can. So these would be plotted on the x-axis. All right, let's do number 3. A equals, B equals, C equals, B squared equals, 4AC equals. A is 2, B is negative 3, C is negative 4. B squared, so that's negative 3 times negative 3 is a 9. 4AC, so that's 4 times 2, which is 8. 8 times negative 4, so that's a negative, and I just said 8 times 4, right? Yeah, which is negative 32. So now we're going to plug it in. X equals negative b, but a negative of a negative 3 is a positive 3, plus or minus the square root of b squared minus 4ac, which ends up being a plus 32, all over 2a. 2 times 2 is 4. You got to add those numbers in the radical. So 32 plus 9 is 41. over 4. We look at the radical. We say, can I reduce 41? Can I split 41 into a perfect square and a number that's not a perfect square? I can't. It's not divisible by 4. It's not divisible by 9. It's not divisible by 16. It's not divisible by 25. So no, I can't, which means my final answers are 3 plus the square root of 41 over 4. And then it's conjugate of 3 minus the square root of 41 over 4. Last one we are going to do all together. First we go a B, a C, a B squared, and a 4AC. Label what those numbers are. We got a 2, a -7, and a 12. -7 times -7 is a 49 for B squared. And then 4AC, so 4 times 2 is 8. And 8 times 12 is, I'm going to get my calculator because I'm not so good at mental math. 8 times 12 is 96. So then I fill this into my quadratic formula. X equals -b. Well, -b is already a negative, so it becomes a positive. Plus or minus the square root of b squared, which is 49, minus 4ac, which is 96, all over 2a, which is 2 times 2 is 4. We're going to add the numbers up in the radical. So that's a 49 minus 96. 49 minus 96 gives me a -47 all over 4. I see a negative in the radical. Remember, our new rule from today is no negatives in the radical. And to avoid negatives in the radical, we write i's now. We write imaginary numbers. So that becomes an I root 47 over 4. We see if we can reduce the radical. 47 is not divisible by any perfect square. So again, check. 47 divided by 4, no. 47 divided by 9, no. 47 divided by 16, no. 47 divided by 25, no. So it's not divisible by anything. It's not reducible. So it is what it is. X equals 7 plus I root 47 over 4. And its conjugate is 7 minus I root 47 over 4. That's what the plus and minus are. Remember, the plus is here, the minus is here, and there's our final answer. Looks horribly messy, but it is what it is. These are imaginary numbers, so that means that if I was to plot this, there are no x-intercepts. And there's our lesson on quadratic formula and what to do when we can't factor to get solutions of quadratics. Thanks for listening today, guys.